Thank you very much. Thank you, Antoine, for introduction. And also, I'd like to start by thanking the organizers, particularly Abhishek, for inviting me to give this talk. And it seems like I have very little to match with the trajectory part of quantum mechanics, although I will be mentioning, but it will be very little. So the talk would be mostly about non-Abelian anionic system in particular, how the quantum information properties essentially we can characterize. And here, obviously, I will not be dealing with how to prepare non-Abelian system from probably parafermions or spin systems, or even how to do interferometric measurements there and so on and so forth. It's more about like I give you a theory and I give you certain constraint behind that theory, and based on that, if I can say something about its information theoretic property. So here is the outline. So first I will talk about something called charge superselection rule, and then I will move towards the simplest and possibly accessible non-Abelian anionic system that is known as the Fibonacci anion. And then I will talk about the correlation there and some ambiguities, and then I will talk about quantum teleportation. In particular, I have two systems, or let's say two parties, and I would like to show that given the same state shared between these parties, one party would be able to teleport perfectly, quantum information perfectly, but the other party will not be. So in that sense, we would like to show that there is an entanglement asymmetry. So let me start with a bit of motivation in a sense, although I don't know much about it in details if you ask me about the physical system behind them, but there are a lot of talks and hypes related to something called topological quantum computation, and these are the early papers we have, essentially, particularly the non-Abelian ones. More specifically, the Fibonacci ones are considered to be the most prominent candidate for topological quantum computation. Here, the term also often we associate like fault-tolerant quantum computation. And there are also some interesting works that are saying that how this system may be simulated or may be created using Cornish matter systems. And recently there are also papers to simulate particularly the Fibonacci anions using superconducting processors, although I really don't know much about the details behind them. So, so my motivation, if I ask, so essentially what my motivation here is that, let's say once I give you some indistinguishable particles, and they satisfy, or let's say they follow certain properties or statistics, what are the consequences one may have in the context of information theory? So if we start with fermions, we know that due to spin statistics theorem, there is something called parity superselection rule, and it says that you cannot have a coherent superposition between even number of fermion with odd number of fermion states. Essentially, then you will not be able to precisely characterize the parity of the state. And that is why we also say that boson and fermion cannot superpose. And this is where essentially you have that it's not only restricts the physically allowed state, it also restricts the operation so that it does not create any coherent superposition between even and odd parity states. And this has been indicated quite long back, nearly 10 years or more that before. So it kind of shows that if you really want to come up with a reasonable information theory with fermions, you need to actually invoke certain context in the context of, let's say, certain relativistic aspect in it. And later on, it has been even further pointed out by connecting it that if you don't take into account relativistic aspects, then essentially you will violate microcausality. And based on that, we also have some work and show that, well, even the operations there has to be restricted. So only a certain set of operations are allowed in the context of an information theory that you do with fermions. And now the question obviously comes, what could be the cases or what we can expect from anions in particular? Because the moment you go with anions, there are certain superselection rules too. It says that the conservation of total topological charges. And there are also a lot of work. Initially, these are by like Aharonov, Susskind, and also Wigner and co-workers. And essentially building on that, saying that, okay, let me accept this fact that this anionic system essentially conjure charge superselection rule, which means that there should not be any, or it's not allowed to have some coherent superposition between states having different topological charges. What kind of ramification or what kind of consequences we may have? Well, it's not only restrict the states, it's obviously on the other side restricts the physically allowed operations. So this is essentially the context of the talk. And now I shall go towards the non-Abelian Fibonaccianians, particularly non-Abelian anions. And there are a little bit of notations here, otherwise it will be very difficult. And as I was mentioning, these are the only part of my talk which has some, let's say, artificially created trajectories, where an anion, let's say C, is splitting in two over time here, A and B, or on the other way around, A and B combines or fuse to give you a resultant anion that is C. And these are the fusion rule in particular for Fibonacci anions. It says that, so E's here are denoting the trivial charge, or sometimes we call it vacuum charge or identity charge. So it says that if you come up with two identity charge anions and you fuse them, it essentially gives you nothing. In a sense, it will give you a trivial anionic charge. And this tau, so essentially we have two kind of charges here. These are the vacuum, or this is the quasi-excitation, and these are the fusion rules. So tau fuse with E, it will give you tau, and the other way around, E fuses with tau gives you tau. However, whenever you fuse tau with tau, it can give you two charges. One is the vacuum, another is the tau charge. And these can be denoted, just for my simplicity, essentially in terms of bracket notations. These are the cases where you see the first two arguments are essentially this left-hand side, and the second or the third argument is essentially on the, about the right-hand side. And it's quite clear from this itself is that, obviously, if I start with two anionic system, each having so-called, let's say, two states, I can create essentially five states, five orthogonal states out of them. And in that sense, it is, if you just look at the dimension of the Hilbert spaces, this itself gives you a difference, or you can kind of immediately see that it will be something very different from if you consider two fermions or possibly two qubit systems. And the dimensions are essentially follow some Fibonacci number, and that's why they call is Fibonaccianians. And here, if I want to take into account more than, let's say, two anions, or more than two or three or something, so then you can also come up with an equivalent bracket notation. So here it is like that the G is splitting into A and B, and then A is splitting into A1, A2, B is splitting into B1, B2, and so. So this is essentially, you can go from the right to the left, and this is exactly the sequences you see. And this is the bracket notation. Apart from that, once you look at the basis, unlike what you have for a qubit system, the bases are not really associative. In a sense, what it says, like if you have G splitting into D and C, and then D splitting into A and B, is not really equivalent to G splitting into F and A, where F is splitting into B and C. So essentially, these are not really associative, the bases essentially. And how to take into account are actually determined by these F matrices, which are essentially kind of a unitary transformation between different sets of bases. And whenever this G means the total charge that you have is the vacuum charge or the trivial charge, then this is nothing but a kind of a diagonal matrix at the end of the day. Well, so using, now coming back to this charge superselection rule, now I can immediately say that, well, that means the only possibilities of superposition that I may have is either between the global charge that's to be vacuum or the global charge that is to be, let's say, tau. So obviously that means these are the only two possibilities. You cannot have a state like this one superposing with this one, because that will immediately violate your charge superselection rule. And from that, so apart from this, obviously you understand that all the operations, physically allowed operations that are there in this theory, obviously should not allow such superposition to take place or be created. And that is why even the structure should also have some kind of a block diagonal structure, each acting in one charge sector. one for E, another for tau. Well, little bit more. Now that I would like to go towards quantum teleportation, and so I have to introduce a little bit more. So I'm saying that, let's say I have, let's say, an operator acting on, let's say, A1 and A2, they're denoting two anionic systems, and I would like to extend it to a larger Hilbert space. In a sense, it's acting on a larger Hilbert space. For qubit, normally what we have, let's say I have I and J, and then I take a tensor product with some identity which is denoted by this. In the similar manner, we can also do it here. Like I have A1 and A2, and this A1 and A1 prime and A2 prime, while having the same charge in this particular case, but it can be arbitrary too. So this can be extended in this manner. And if I have a simple, let's say, unitary, which is acting on one anionic system, that means it can at most be a diagonal matrix because of different charges. This also can be extended in this manner, where the basis will be, as you can see, you can follow it from that these correspond to this basis. It will still be a diagonal matrix. These correspond to these correspond to these, and so on and so forth. And on the other side, you can also have a partial tracing. If you have an operator, let's say A1, A2, B1, B2, where A1, A2 corresponding to two anyons, B1, B2 corresponding to another two anyons, and from there I would like to go to the space, the operator acting on the space A1 and A2. Obviously, I can take out the B part, let's say trace out the B part, and this is essentially the rule. And if I give you a simple example here, let's say I have A1, A2 with global charge G, and then A1 prime, A2 prime with global charge G, I can also reduce it back to A1 and A1. And what I want to highlight here is that this G has something to do with like having some kind of a global property coming from A1 and A2, but once I trace out this G, the information that is there in G is gone. Well, now I'll talk about correlation a bit, and particularly I would show that it's also giving you something fundamentally different compared to what you have for boson, fermion, or qubit systems. For example, consider this particular state. So this is an allowed state where the global charge is a tau, and they can superpose and so on and so forth. It looks like, obviously this is orthogonal to this one and so on and so forth. It looks like it's an entangled kind of state, but if you take a partial tracing, let's say on A, or partial tracing on B, that means the reduced state rho A, you see it's a maximally mixed state. On the other hand, if you take partial tracing over A, the resultant state is actually a pure state. So this is already an important observation in that sense, because whenever you have an entangled state, the marginal spectra should be same. But here you see that one is pure while other is really mixed. So this already questions this particular point that, well, so the traditional sense of Smith decomposition is also not going to work here. You have to take into account much inner algebra essentially to really figure it out. And for the same manner, if you want to quantify your entanglement for anionic system, you have to be careful with this point. And it's not all. Essentially, even if you start with a classically correlated state, as you can see, it's a mixture of a state between a state which is in the E charge sector and another is in tau charge sector. And if you trace out one party, and you see that the reduced states are essentially pure state. So this again says that if you start with a mixed state, your reduced states can be pure state there. So this again kind of tells you that if you consider this kind of anionic system and you try to say that, well, the entropies, let's say the von Neumann entropy is having something to do with coding theorem, and so you have to be a little bit careful here, because the reduced states here obviously is not mixed state. So that means the probabilities, particularly the information contents, are not directly one-to-one correspondence you may not have. Well, with this, now I will talk about the correlation that is there in the anionic system. And one of them is like the rudimentary definition that we have is that if I have a joint state rho AB, and if I have two local observables there, and the expectation value, if it factorizes in this form for all possible OA and OB that are the observables, then I call it uncorrelated state. And it turns out to be, using this definition, that essentially the states I was talking about earlier also, that this particular state is essentially uncorrelated. I think this is, yeah, So this particular state is uncorrelated if alpha is equal to 0 and beta is equal to 0, else it is correlated. In the same manner, if I have another generic state in this charge sector tau, this is the case. If my alpha tau, so that means if this is 0, if I just have these two states in superposition, this is also uncorrelated state. On the other hand, if I have this particular beta tau to be 0, then a superposition between this and this, although it looks like entangled, but it's actually uncorrelated, following this particular definition. However, another important point here is that given that I have this charge superselection and all the states cannot superpose with each other, the only so-called maximally entangled states are essentially these one. And if you can see that I don't have any term coming from tau, tau, and tau. So these kind of states. And this kind of says that even though I'm dealing with two anionic systems, but these maximally entangled states, they essentially do not span the entire space because I'm still left with this particular state which is not captured by these two. Well, so these are the differences I have. And now let me just show that, well, when I say there is some ambiguities there in the context of entanglement and so, obviously I have to operationally prove them. And for that, I will be choosing quantum teleportation. And the argument here is that if I can do quantum teleportation, that implies there is some entanglement. If I don't, that implies that there is no entanglement as such. And all these I will be doing essentially in terms of pure states. So there is no ambiguity as such as well. So let me now consider, like, there are Alice and Bob and sharing this particular state. And if you look at carefully, essentially it gives you symmetric marginal, in a sense like having same marginal spectra. Okay. And this is the message, let's say Alice wants to teleport to Bob. Where I say message, it's essentially these two complex numbers, alpha and beta. And so obviously the joint state, I understand that this may be a little difficult to follow, but just for completeness, I'll be showing them. If you have some question, I can come back to them. So essentially what you have, if you have your M state coupled with this R state here, and this is essentially the resultant state. But remember, the anionic states are not really associative. In a sense, this particular state and this particular state, they don't look the same. You have to really transform them using this F transformation, F move transformations. So from here to here, if you go, essentially your state look like this. Well, anyway, so you may not need to really follow that in details, but what I wanted to say that once I club this M and A together and B is there like this, I can essentially express my global state in this form where this lambda plus minus and eta plus minus are essentially orthogonal bell-like states. And now I do a measurement here and do something here. At the same time, I do some measurement here and do something like we do in typical teleportation protocol. And accordingly, if I apply some local unitaries here where the Z is denoted in this manner, I can essentially recover the message, or the Bob can recover the message alpha and beta. So there is actually a perfect teleportation from Alice to Bob. On the other side, if let's consider Bob wants to, using the same resource state and the message accessible to Bob, Bob wants to teleport to Alice. Once again, I will be doing the same thing here. Alice and Bob was initially together, and then M is being attached from Bob's side. And then again, I will do some F move transformation where I club this message with Bob in this manner. And now, if I look at very carefully, because of parity superselection rule, essentially the Alice state can never be in a superposition of this and this. It will always be in a probabilistic mixture, however, or whatever measurement that you want to do on Bob's side. So in a sense, what I wanted to say is that I can never be able to come up with bell-like measurements on Bob and message state. And because of that, there is absolutely no possibility of quantum teleportation from Bob to Alice. So this is essentially to say that, so if I come from this rule, like what is the charge superselection rule together with the fusion rules, these two itself is kind of restricting, saying that, see, I have Alice and Bob sharing the same state, but access to the entanglement by Alice is very different from access to the entanglement by Bob. So there has to be certain thing which is asymmetrical. And this is with, I would essentially conclude, it says that the charge superselection rule and the fusion rule has obviously some deeper implications in anionic quantum information theory, and obviously this should also be manifested in their operations. There is marginal spectra ambiguity and also the ambiguity of global and local spectra. So in that sense, it says that the typical way of counting the information encoded in the states obviously has to be reviewed. And also the correlations, like you cannot really use the traditional way of characterizing correlation for anionic system, particularly for non-Abelian ones. And for bipartite pure entangled state, you don't have equal access of entanglement by the parties. And obviously, if you consider these to be true, obviously this will have some deep implications, or let's say applications in communication or cryptographic protocol, where one party has a lot of control over the other, but the other party does not have. Well, so these are the conclusions. And another thing I would like to add is that the observation that we have is very generic, in the sense, for almost all non-Abelian anionic system, you will see this kind of disparity. For example, we checked with even Ising anionic system, and this shows a similar behavior. Well, before I end, I would like to want information for all of you. So recently, it's a little bit about science and society, not just science. So recently we established a platform called International Union of Scientists, where the scientists are against militarism and destructive use of science. So I would request you people, if you are interested, to look at this website. It's essentially to say that while we do science, we hardly care about how our research and technology are being used to kill people or for destructive purposes. Here also we essentially, it's yesterday only that we sent a call for contributors. If you want to participate, please do join. And what I just wanted to say is that we are scientists, at the same time we are human beings too. And we should care for society. And this is a photograph. It's essentially a photograph coming from a refugee camp, a little girl essentially offering food to a journalist when the journalist was trying to take a photo. So with this appeal, so that let us be a little bit more human, more concerned, let us not be restricted only just to our laboratories, at least care for what is going on around and whether we are complicit directly or indirectly in that. So with this appeal, I would like to thank everyone for your attention.
Are there questions about the talk? Otherwise, I can start with one. So for fermions that are like fundamental particles in nature, I understand why the charge superselection rules are strictly enforced. But for anyons that are going to be realized as effective particles, probably in mesoscopic systems, so they are not going to be fundamental particles. They are going to be realized probably from standard particles. Is it so clear that these charge superselection rules will also be there, or that we won't be able to construct
okay, it comes from essentially this anionic field theories, or let's say these non-Abelian field theories. It says that whenever you come up with these restrictions, the only very specific values of charges are allowed. The moment you have two different states coming with two different charges and they superpose, that means there will be an ambiguity. You cannot precisely define what is the charge, and these are not allowed by the theory.
Okay, so we do expect that if the system is well described by a topological field theory, this will be strictly enforced. Okay, thank you. Are there other questions? Yes. Okay. Is there a microphone close to you? Otherwise, I can't.
Hi, thank you for your talk. When you talk about the entanglement between the anion, my question is, So you showed that when you trace out one of them, when you look at the subsystems, one gets more affected by the entanglement, one doesn't. But I didn't fully understand what causes this disparity, and how do we know one gets mixed and one remains pure, for example?
Well, it turns out why it is happening, if you say, it's just the consequence of your charge superselection rule and the fusion rule, okay? And now if you say that, how do you know if it is happening or not? So this is, you know, by, let's say you do local measurements there and try to see how the states are appearing. Let's say you do, so for example, for anionic systems, you can do measurement of some fusion channels using some interferometric experiments. So you look at the state, and if you see that it's appearing to be a pure state, that means you know it's pure state, right? If you look at on the other party, so let's say Alice and Bob sharing, let's say one state, and you look at your state. Let's say Bob is looking at it, and if it finds it pure state, but Alice may find it, let's say mixed state. That's how you find it. Is this your question?
So, but then you never know, I mean, at least one of the parties will never know if their particle was entangled or not, right?
A priori, you may say yes, but now let's say they can check it just by using teleportation. It's an operational way you can check it.
Okay.
Yep.
Okay, any other question? Okay, otherwise let's thank the speaker again.
Thank you.
Cool.